So last time, that is yesterday, we stopped at the Maxwell's equations and we were talking about the contribution from Maxwell, and that was the introduction of a component in the current or the current density coming from the displacement current. And this contributed to the wave equation that is used to study electrodynamic effects in nature. So today we are going to look at the reduced Maxwell's equations, and we say that these are usually important, especially when we have situations where we have like an axis of symmetry. And therefore the applications of the boundary conditions becomes much easier when we have these kind of cases. So the electrodynamic fields can therefore be expressed in terms of an axial and transverse components. By transverse, we are saying they are transverse to that axis of symmetry. So how we are going to do it is that we are going to consider an electromagnetic wave that is propagating in the positive z direction, where by implication we are choosing z to be the axis of symmetry that we shall be using. So the fields are then assumed to have a harmonic time dependence and an exponential z dependence of the form given as the exponent of j omega t, that is a sinusoidal kind of variation with time, and gamma multiplied by z, where gamma, okay, that exponent of j omega t minus gamma z is usually called the propagation factor of the fields through the space. And we must have met it. It's usually given as alpha minus j beta, where beta is usually called the phase propagation constant and alpha the attenuation constant. And therefore, once we make that kind of assumption where we are using an exponent, then it means that we'll simplify our solutions very easily, because now the derivative with the special derivative with respect to z is just given as minus gamma, and the time derivative is just j omega. And therefore, since we know that the Maxwell's equations are all differential derivatives, then we can always replace those derivatives using the given constant that we have there for the particular components. And therefore, the del operator can be split into two components. One, a del operator that operates in the transverse plane, and an axial del operator, which we replace by its value, that is minus gamma, and therefore we get del t minus z gamma. The electric field and the magnetic fields, that is in fact all the fields, can therefore be split into two components. One, a transverse electric field component and an axial field component, and the H as well as the others. The D is related to E. We are going to assume it's related to E by a constant epsilon multiplied by E, where epsilon, but for this time we are not going to say anything about it. In many cases, it depends on the material that we are dealing with and the material properties, and in many cases, epsilon may become a matrix, or what we call a tensor. J, which we assumed that the convection current is no longer being considered, we are just considering the flow of charge carriers in a conductor, then J, that is the conduction current density, is going to be given by sigma multiplied by E, where sigma is the conductivity of that material. And beta, or B, or the magnetic flux density, is going to be given by the permeability of the material multiplied by the magnetic field intensity H. This is also usually a complex number, but for the media that we are going to be dealing with in this particular course, which are said to be homogeneous, linear, and isotropic, they'll have a constant value, and therefore they'll be called scalars. But in case you are dealing with materials that are none other than simple, then you might have to use a tensor for mu and a tensor for the electric permittivity epsilon. So Maxwell's curl equations, that is the Faraday's law and Ampere's law, then become of the following form. The curl of E was equal to the negative time derivative of B, and we'll replace B by mu of H, and therefore the curl of E is equal to the minus of the derivative, the time derivative, which we replace by the J omega. So it's minus J omega of mu into the transverse magnetic field intensity plus the axial field intensity Hz. And on the other side, of course, we are splitting also the del operator into its components there. And now what we are going to do is to spread the values through. So I'll give you a minute to try and open the brackets on this side of the equation, and then we can show how it comes about. 1 minute, please. Here, I'm assuming that we are conversant with how to deal with vectors. Just treat them. Don't worry what they are. Just treat them as vectors. We know the del operator is not really a true vector, but just open up the brackets according to the the vector calculus kind of rules. So if you have already done it, all we have to do is to just say like it was going to be the transverse curl of the transverse electric field minus the Z, and we give it as follows. That is for the H field, and then we shall have the following cases. So to open the brackets, we'll get that we have a transverse curl of the transverse electric field minus Z. What I did is that we had before the curl of Z cap of Ez, and then I use the vector rule that I can interchange the two equations or the two whatevers. And here there should be a cross product here, although this doesn't appear here. This is a mistake. I'll have to correct this in the whatever I send you. So there is a cross product here, or the cross symbol that is missing there. It's not just Z into the bracket, but it's Z cross that argument in the brackets there. And therefore, we can see that from the cross product rule, the cross product of two vectors is usually another vector that is normal to the plane that contains those two vectors. And therefore, since E is transverse is in the transverse plane and del T is in the transverse plane, the normal vector to that plane is therefore the Z. And therefore, we can see that this particular component can only be equal to the axial component of H of Z. And therefore, we see that the transverse curl of the transverse component of E is equal to the minus of J omega Z cap and H of Z. And for this particular case, this is the way it should appear: Z cross del T of Ez plus gamma E of Z of T must be equal to J omega mu and the transverse component of H. So we get two equations, one for the transverse, for the axial component of the magnetic field, and one for the transverse magnetic field. Similarly, in the Ampere circuit law, we have a similar kind of things, and we again see that the axial component of the electric field is given by the transverse curl of H of T and given by the conductivity plus J omega epsilon of Z is a cap. And for the transverse component, we have that following case. So this forms the reduced Maxwell's equations for the curl, for the Faraday's law, as well as the Ampere circuit law. So we can put this together in the reduced form as follows. One, the Faraday's law of induction. We have that the axial electric field, magnetic field intensity is related to the transverse curl of E of T, and the transverse magnetic field component is proportional to that Z cross of that argument there. And the Ampere circuit law is again given as follows, and with a negative sign. What we have to show is to see is that for Z cross, we have no negative sign here, while we have a negative sign for the curl. Here, we have as usual, but the Z cross has a negative sign. We shall see that this is a little bit opposite to what we always get, but we can always correct that by multiplying through by the Z cap. In Gauss' law, we again do the same and see that the divergence of B, which we replace by epsilon E, is going to be given by rho by epsilon there. That is, the transverse divergence, or the divergence of E of T in the transverse plane, is equal to the volume free charge density over the electric permittivity plus gamma multiplied by E of Z. The divergence of B, we said, was identically going to be equal to 0, and therefore we see that in the transverse plane, the divergence of the transverse component of H of the magnetic field intensity is just equal to gamma of Hz. So, how do these transverse fields, we can always express the transverse field components of the magnetic field and the electric field in terms of only the axial components. And this is how we are going to do it. So, if you look at the H of T, we can evaluate a cross product with Z cap, and we have it as Z cap cross the bracket Z cap and cross of that equal to that value. So we open up the brackets using the back cap kind of rule. You remember the vector multiplication rule, and therefore we should get that we have Z cap into the what we are multiplying with times the dot of that minus that value here. If you can recall A cross B cross C, all we are saying is that it's B into A dot C minus C into A dot B. And therefore, what we can see is that Z is an axial field. That value there is going to be a transverse value, and that is also transverse to Z. And therefore, since this component here and that component there are orthogonal to each other, then the cosine is going to be equal to 0, and therefore this particular part of the equation goes to 0. And this just goes to unity, and in the end, we are just left with the following, that the transverse gradient of the axial component of the electric field intensity plus the gamma multiplied by the transverse electric field component is equal to the minus j omega mu of z cap cross h of t. And this is an important relation to keep in mind. Now, we apply the expression for E of t, that is, we multiply the expression for E of t by minus j omega mu and divided by gamma, and we open the brackets to obtain the following. This is the equation that we are talking about, the equation for E of t following the magnetic field intensity. So we multiply it with this value here, and since it was negative, of course, it becomes positive now. And on the other side, we multiply again as given, and we open the brackets through. So what we get is that we get the following, that the minus j omega mu of z cap cross h of t is equal to that value plus z cap multiplied by that value and del t of h of z. And therefore, once we see this, we can always add it to this equation that we have here, or subtract from this equation that we have here, and we'll have everything coming out properly. So we can eliminate the transverse component of the magnetic field from the resultant expressions through subtraction to obtain that the gamma of t, E of t is equal to that equation there that we have there. Or in other words, we can put the things together, that is, we get the values of E of t, put it on the other side, and we leave only those remaining. And we see that that is going to be given by that. And we can therefore simplify, and we get that the minus of gamma over gamma squared minus j omega mu into sigma plus j omega epsilon multiplied by the gradient, the transverse gradient of E of z plus j omega mu over gamma squared minus j omega mu into sigma plus j omega epsilon multiplied by the z cap cross the del, or the gradient of h of z in the transverse plane, will be equal to the value of E of t. In other words, we can always replace this expression here, gamma squared minus j omega mu into sigma plus j omega epsilon, by a new constant, which we shall call a constant of propagation, and call it k of c. And therefore, this will be replaced by k of c squared, and therefore the equation becomes an easier to see, or an easier to absorb kind of expression that is shown here. So this is the way we'll come about it, and this is what we shall be seeing. In many cases, sigma can be absorbed in epsilon by using a complex number for epsilon, or sometimes in a medium that is lossless, that is, does not attenuate or dissipate power, then sigma is going to be 0, and then we shall see that the k of c will now become like gamma squared plus omega squared mu of epsilon. So in many cases, we won't have it as it looks here, but this is the general case for a general material. So similarly for the magnetic field, we'll do the same. And that I can give you 2 minutes to try and reduce it the way we have done here. Try to see whether you can get it as it shows there. Don't just copy the expression given, but try to work it through. That is, you take the Z, the cross product of Z with the equation for the transverse electric field in terms of the H field that we saw before in the ampere circuit law. So you can try that and we see whether you get it. So are we in? Are we trying to do it really? So I'll just continue since you are not cooperative. So we can say that when we do this, we get h of z as shown there, and we multiply the h of z by the sigma plus j omega epsilon by gamma and open up the brackets so that we reduce that into the same kind of the value before. And our object is to try and eliminate E of t from the equation of h. And what we get is the equation as follows. And by subtraction gives us the following. We get that h of t is equal to the minus of gamma by kc squared, the transverse gradient of h of z minus j omega epsilon minus j omega mu and of kc squared and the z cross the transverse gradient of E of z. And therefore, the object we were looking for is to express E of t and h of t in terms of the axial field components alone. And what does this help us with? It tells us that if we know the transverse component or the axial components of the fields, that is the electric and magnetic field intensities, then we know what the transverse components are going to be. We can always get them using those expressions. This is usually called an axial-transverse plane kind of split. So, just like before, we have h of t is given by minus gamma by kc squared, that, and so forth. Now, since we have already, the other expressions, of course, will reduce as well once we use the appropriate components of the del operator and so forth, and it becomes much easier to see. We have already seen what those ones are going to be. Now, another important theorem that is going to help aid us in understanding the fields in this particular case is how to know that the field, if we solve a problem and we get expressions for the fields, how do we know that we have completely specified these fields? This is done with the help of Helmholtz theorem, which says that a vector field is completely specified in a region of space to within an additive gradient of a scalar field if both its divergence and curl are known everywhere in the region. The reason why we are talking about the gradient of a scalar field is because if we take the curl of the gradient of a scalar field, that is a vector which is a gradient of a scalar field, that is going to be equal to 0. And therefore, we can always specify a vector and add to it a gradient of an arbitrary scalar field for that region. And if we take the curl, that will not have changed the definition of the field that is defined as the curl of that particular field that we have defined. So Helmholtz theorem allows us to know the field itself to within that value. And all we need to do is to specify its divergence. If we know its divergence and we know its curl, then it's known everywhere. So any general, say for example, for the electric field, we have seen that the curl of E is equal to the negative time derivative of the magnetic field in magnetic flux density. And we have seen that the divergence of D, or the divergence of epsilon multiplied by E, is given by the volume, or the free volume charge density divided by epsilon, or the electric permittivity. And therefore, E is specified within that region we are dealing with. Similarly, for the magnetic field intensity, we know that its curl is given by Ampere's circuit law, and its divergence is identically 0. And therefore, we know that the magnetic field is completely specified, and the electric field is completely specified if we know the volume free charge density in that region that we are dealing with, and according to Helmholtz theorem. Now, what we can say is that any general vector field can be decomposed into two components. One, a component with a curl that is identically equal to 0. If the curl of a vector field is 0, is always 0, we say that that field is irrotational. That is, it doesn't have a curl. It's curl-free or irrotational. And we can have another component whose divergence is identically 0. That is, that component, or a field with a divergence that is identically equal to 0, is usually called divergenceless, or it's called a conservative field, or a lamellar field. Say, for example, the gravitational field is usually a lamellar kind of field. It doesn't have any, if you do an integration, it does not depend on the path of integration. So, like I said, a divergence-free field is called a solenoidal field, while a curl-free field is said to be rotational or lamellar. I think I may have used the wrong words previously. And therefore, consider a vector field F that is arbitrary. All it says is that we are going to use to split it as F equal to the curl of a vector field A plus the gradient of a scalar field phi. A and phi are analytic vector and scalar fields, and we want them to be analytic so that they have derivatives. That is, since the dial operator is a derivative operator, then they must have a derivative, and in that particular point where F is being defined. Now, if F is solenoidal and as well as rotational, then both its divergence must be equal to 0 and its curl must also be equal to 0. An example of such a field is usually the electrostatic field in a charge-free region of space. That is, we are looking at a dielectric that is lossless, doesn't have a free charge carriers, and therefore when we do its curl, we are going to get a 0 because the field does not change with the position, and 2, its divergence is also going to be equal to 0. Now, since the time derivative is equal to 0, then the dB dt is equal to 0, and that's why I have that the curl of E in the Faraday's induction law is equal to 0 for that particular case. And when we take the divergence of E, it should be equal to rho by epsilon, but since we are talking about a charge-free region of space, then that one becomes 0 as well. And therefore, F will be described as both solenoidal and rotational, or divergence-free and curl-free. F could be solenoidal, but not rotational. This happens when the divergence of F is equal to 0, but its curl is not equal to 0. An example would be the magnetostatic field established by a time-independent current, that is a DC current flowing through a conductor. This, according to Ampere's circuit law, it will establish a magnetic field surrounding or going around that particular conductor. And therefore, the curl of the magnetic field intensity must be equal to the total current density in the conductor, which is equal to J. And we see that the curl of H is not equal to 0. But we already know that since there are no magnetic charges anywhere discovered, the divergence of H is always equal to 0. And therefore, the magnetic field or the magnetostatic field is solenoidal, but not divergent or irrotational. F is solenoidal, but not irrotational if, I think this one is wrong here, that is, F is not solenoidal, but irrotational, and not irrotational if we have the following. I think that is okay. The curl of F is equal to 0, but its divergence is not equal to 0. An example would be an electrostatic field in a region of space containing charge, in which case the curl of E is equal to 0, that is curl-free. This is not correct here. It should be irrotational here. And this is rotational. And we see that the divergence of E is equal to the free volume charge density in the region of space divided by epsilon. Okay. Now, The general case is when F is neither solenoidal nor irrotational. That is, both the divergence is not zero and the curl is not equal to zero. That's the general case. But we can always split it into a component that would be irrotational and a component that is solenoidal. An example for such kind of a field is the normal electrodynamic waves that we shall be dealing with, which has free charge, in which case we have the following, that the curl of E is equal to the minus mu d dt of h of t, that is the minus time rate of change of B. This t is unfortunate, should be there. And the divergence of E is equal to the volume charge density divided by epsilon. In some field problems, we'll find that we'll have to satisfy boundary conditions in that field, in that region of space. In some cases, you may need all the components of the field. Since the fields are three-dimensional vectors, all the components will be required for the given boundary conditions to be satisfied on such boundaries. But in some problems that we shall be facing as we study electrodynamics in this course, we shall find that there are conditions where not all components are required for the given boundary conditions. And this is what now makes the splitting or writing the Maxwell's equation with the reduced form very useful for us. So we can have one, that the electric and magnetic fields in the axial directions are identically equal to zero. That is, the electric and magnetic field intensities are everywhere transverse to the propagation, the axis of propagation. Such kind of a field or a wave is usually referred to as transverse electromagnetic wave or TEM wave. And this is the wave that you'll always get, especially when you are studying in the third year course. You dealt with what we call plane waves. Plane waves are usually waves that have the electric and magnetic field intensities normal or perpendicular to each other and perpendicular to the direction of propagation. We can have transverse electric fields, in which case the axial electric field intensity is equal to zero, but the axial magnetic field intensity is not equal to zero. Such kind of cases will appear especially when we have an electric field or an electromagnetic field that is being confined to flow through some certain boundaries. Say, for example, between two parallel plates, or inside a hollow rectangular or circular conducting pipe. That we will always have an EZ and HZ that is not equal to zero, and as HZ that is equal to zero. And at the same time, we can have the opposite, where we have a transverse magnetic or E wave solution in which EZ is not equal to zero and HZ is equal to zero. This will be the topic that we shall be dealing with in the second semester when we talk about waveguides or structures that guide waves along a desired direction. So when you are faced with some problems, especially when we have discontinuities in the material properties, then you'll find that there will be no preferred x-axis for that particular wave. And all the components of the fields will be required. In such kind of cases, we have Ez not equal to zero and Hz not equal to zero, and therefore we call this a mixed or hybrid wave solution, in which case both TE and TM must be considered when we are dealing with that particular problem. Now, this classification of electromagnetic waves as either TEM, TE or H, or TM or E waves is we have to choose the boundary to be parallel to the axis of propagation. And in that case, once we do that, then we can have that either EZ or HZ is going to go to 0. And we can therefore remove that component out of the equation. Or we can use those ones as the continuity of those components to define what the fields are going to be in the solution. So we look first at what we call the TEM waves, or the transverse electromagnetic waves, which are normal, just like the light that comes from the sun. So the transverse electromagnetic or TEM waves, the EZ and HZ are identically equal to 0, and therefore in the reduced form, we can have Faraday's and Ampere's laws having the following form. We saw that the transverse or the axial component of H was given by the transverse curl of the transverse component of E. And therefore, since H is equal to 0, then we can have that the transverse curl of E, or the transverse electric field, is identically equal to 0. And we can see that the gamma of E of T is equal to the minus j omega mu and z cap cross H of T. And again, for the Ampere's law, Ez is equal to 0, and therefore the transverse curl of the transverse component of magnetic field intensity is also equal to 0. And for the transverse fields, we can have that kind of expression there. So now E of T and H of T are irrotational because the curls are all equal to 0 in the transverse plane. And therefore, using the vector identity that the curl of the gradient of a scalar function, that is, the curl of a vector field that is a gradient of a scalar field field function, is identically equal to 0. So once we get that, then it means that since they are irrotational, we can always define them as gradients of a scalar functions, which we'll call phi of E and phi of M. The negative sign here is placed there by convention, because once we derive the fields from this definition, the voltages and currents measured in the laboratory will be in the right direction. Okay, so this negative sign here is put there by convention to make sure that observation and the mathematical definition tally or are consistent. Now, we recall that for fields that have sinusoidal and exponential variation in the z and time, then the gradients, that is, the derivative, the special derivative in the axial direction, is just minus gamma. And therefore, we can write that gamma of ET is equal to that minus j omega mu z cap. And therefore, we can replace this by this value d dz. Now, if we replace E of t by its definition, then we see that the gradient of the special derivative, or the derivative of the phi of E with respect to z, is equal to the minus of j omega mu. Okay? Remember that phi of E we'll call it the electric scalar potential function, and phi m we'll call it a magnetic scalar potential function. So we are not replacing that as yet, because we know that this value here can be written in terms of E of t, and therefore we can separate the phi of m and phi of E in the equations. Now, recall that the z cross h of t was given by minus sigma plus j omega epsilon divided by epsilon gamma and multiplied by E of t, because we saw that for that particular case, the values of E of Z and H of Z are equal to 0. And therefore, this becomes simply written as that equation there. And if we place this equation in there, we can always see that the gradients are the same, and therefore the arguments can be removed, and we are just left with the ddz of phi of E is equal to the minus j omega mu and multiplied by pi of E. That looks familiar. If you were to recall from your transmission lines, that is, if we multiply through by gamma, okay, or minus gamma on both sides, what we'll get is that you are going to get the following equation, that the d squared, dz squared of phi of E is equal to j omega mu sigma plus j omega epsilon and multiply phi of E. If you can recall your transmission line kind of expressions, the ones you call the telegrapher's equation, we have that d2 dz dz squared of v of z is equal to the minus of omega squared L multiplied by C and multiplied by the same function, so to speak. So this is exactly in the same form as the telegrapher's equations that you have met through before. Don't get confused by these values here. These are all per unit length kind of values. This is in Henry's per meter, therefore can stand in for the inductance per unit length. This value here is the sigma. This is it's called the conductance that you always got as G prime, or the conductance per unit length for the medium, and that is in farad per meter, and therefore can be a capacitance per unit length as well. And this could be taken as voltage, and then we'll have a given value, so to speak. So we can therefore express this in the form d2 dz squared of v of z equal to z prime y prime v of z, where v of z, or the voltage wave in the axial direction, is defined, is equal by definition to phi of E. We are saying that phi of E be v of z. The z prime is just j omega mu, and y prime is sigma plus j omega epsilon. And these are the per unit length series impedance of the line and the shunt admittance per unit length of the line as well. And likewise, in the value for the magnetic field, we can also do the same. And what we do is that we put the value of the cross product of E of t and z, and as it's shown there, and then we can also have these following expressions, and we drop out the dels and multiply through by gamma, and what we get is that we get a similar value where the second derivative with respect to z of the magnetic scalar potential phi of m is given by sigma plus j omega mu and j omega mu multiplied by phi of m. Again, we see that this one is similar to the other, and now we make some definitions. We can define the values as the second derivative of a current wave equation, or current wave on a line, as given by the impedance, series impedance by unit length, shunt admittance by unit length, and multiplied by I of z, where the I of z is now defined as phi of m, because we know that H is measured in amperes per meter. Therefore, the phi of m should be our current, so to speak. It should have units of current rather than voltage. And therefore, the values are given as before, and they are the same as that for the voltage. And we have two equations, or two wave equations, that with respect to the z. So these expressions, we can say that these expressions are in the same form as the telegrapher's equations for voltage and current waves on a transmission line. And I'm sure in your ECT 322, or 3-1 or 2-1, I think, you must have met this kind of equations before. You used, instead of Z and Y, we were using L, R, G, and C. Okay, that is L prime, R prime, C prime, and G prime. And therefore you had those values as R prime plus J omega L prime into G prime plus J omega C prime and multiplied by the AI of Z. In this particular case, all we have seen is that the Z part does not have an R, and it's because we are assuming that our medium does not have, okay, our line has no losses in the conductor. If it had losses in the conductor, we'll see that those ones can always be corrected for by the magnetic field having a complex value. We'll get an R. So I'll give you 2 minutes to try and absorb that. If you have any question, you can now raise them for that particular part.
Yes, I have a question.
Yes.
In a few slides ago, when we were deriving, we dropped the del operator. Yet
Yes.
on the right-hand side, it did not apply to all the terms, but only to one term.
Let me see what you are talking about. That one?
Yeah, there. On the
But
right-hand.
this term is like a constant.
Oh, so,
Isn't
okay.
it?
Yes.
This is like a constant. So it's like the way, this one is a derivative, all right?
Yes.
So this is the function that is varying with respect to the derivative. And at the same time, it is the same kind of thing. Agreed? We are taking the gradient of the time of the z derivative of phi of n. Agreed?
Yes.
So we could take all these ones and put them in here and take the gradient of some value, say a constant c multiplying phi of n. Agreed?
Yeah.
Since this one does not depend on the spatial whatever the spatial coordinates, then we have put it outside. It's just like multiplying by k, and therefore we can see that that del operator there is the same as this del operator here.
Oh,
So it
thank you.
can be dropped out.
Oh, okay, thank you.
And
Yeah,
that's why I'm multiplying it by k. We are
okay.
going to get equations of this nature where a differential part, the differential equation is equal to the function itself multiplied by a constant. Such kind of equations of problems are called eigenvalue problems. You must have met them when you are dealing with control engineering or mathematics, where you got things called eigenvalues or matrix form of, solving problems. Okay? So they are going to be very important to us as we go along. I hope that is clear.
Yes, it is. Yes, it is.
Okay. Any further questions? So we now look at what we call the TM waves, or in other words, they will be called E waves because these TM waves will be derived from the axial component of the electric field. The Hz is equal to 0, that is the magnetic field is everywhere transverse to the axis of propagation, but the axial electric field is not equal to 0. And therefore, once we specify the axial component of the electric field, all the other components in that wave will be determined because we have shown that the transverse components are related to the axial components of the fields. So, in this particular case, the transverse electric field component is irrotational in the transverse plane. Why it is irrotational is because if we take the curl of the electric field of this transverse electric field component is equal to the minus j omega mu z cap h of z, and h of z is equal to 0. Therefore, the curl, the transverse curl of E of t is going to be equal to 0, and that's why we are calling it irrotational. And therefore, since it's irrotational, we can define it as the gradient of an electric scalar potential, phi of E. It doesn't have to be the same as the one we did for the T of E, TEM, but it's a scalar potential. That's all we are saying. I'm just using the same kind of symbols, but it's not the same function that we had before. So the transverse component of the magnetic field intensity must therefore satisfy the equations that the cross product of the gradient, the transverse gradient of E of z plus gamma E of t must be equal to j omega mu and h of t. And we can see that once we multiply through by the gradients, and that is from the other equations, that h of t is going to be given by the minus of psi of sigma plus j omega epsilon by kc squared multiplied by z of cross del t of Ez. Remember, h of t was given by minus gamma over kc squared multiplied by the gradient of h of z. And since h of z is equal to 0, we are just left with that plus component, which represents the transverse or the axial component of the E of z. That is from the reduced Maxwell's equations. And therefore, once we do that, we can always use the value of E of t that we have into that expression and have it as shown there. Now, we can therefore open up the brackets and leave and take them to the other side so that we are just left with these values alone. And what we have is that gamma of E of t is equal to that value there. Okay, look, notice the z cap cross and the z cross therefore tells us we can always drop out this z cap cross on both sides. It's the same. Okay, it's not just multiplying that gradient there, and this is multiplying that vector there, and therefore once we drop out the z cap, we now are left with the transverse gradient of E of z, which we take to the other side of the equation, therefore it becomes minus, plus j omega mu into this minus value that we have here, which is just multiplying the gradient of that. And we see that that and that are the same. So what we are going to do is to take this one out of the bracket. Okay, we put it outside the bracket, and we see that is going to be 1 plus, and then what we are going to do is to correct this value, okay, by taking it out of the bracket itself. And once we do that, we get the kc squared by sigma plus j omega epsilon plus j omega mu remaining, because this is multiplying that, and then we put them all together in there for ease. Although it's a constant, I'm putting it in here so that we can make certain interpretation of the quantities that we have now. Now, remember that E of t is minus gradient of phi of E. And therefore, since it's being multiplied by gamma, we'll put it as minus gamma pi of E in there and take its gradient. It will be perfect. And then we put the others as shown there. So in the end, we see that this gradient here and that gradient here that can therefore be dropped. And we know that minus gamma is the same as d dz, okay, in our equations. And therefore the derivative of phi of E with respect to z is just going to be given by the minus of kc squared over j omega epsilon I think here I've left out the sigma, but it should be there, plus j omega mu, and multiply by sigma over plus j omega epsilon over kc squared E of z. The reason why it has been dropped out is where we are assuming that sigma is now lossless, or the material is lossless, or we can take this epsilon to be a complex value. So this can be expressed in the same form as before, that the derivative of v of z with respect to z is equal to the minus of z prime multiplied by I of z, where our value, our voltage wave is going to be identical to, is equal by definition to phi of E, and the current is going to be given by sigma plus j omega epsilon over kc squared E of z. So, and z prime is going to be given by kc squared over sigma plus j omega epsilon plus j omega mu. This is a series impedance per unit length. Why is it going to be an impedance? If you look at this, K of C is usually measured as twice pi over the wavelength. So this has the dimensions of per unit area. That is, Kc squared is per unit area. And therefore, since it's appearing at the bottom, it will multiply at the top. This is a conductance per unit length. That is a capacitance per unit length. That is a voltage per unit length. And the areas will cancel each other. And therefore, all we'll get is we'll get a conductivity or a conductance multiplying a voltage. And in the end, we have just a current in amps. And therefore, the Z, if you were to do the same, we'll get that kind of value. So what we can say is that this is similarly given as follows for the H, or for the H field, and we can get those values as shown there, where we are opening up the brackets and giving them from the equations that we had for the reduced Maxwell's equations. So if we multiply through by gamma, we'll get that given value there. And therefore, when we put them all together, we get again a similar kind of equation. Remember, this is the same value that we got before, so we called it a current. And this value here is a conductance, and we give it as gamma prime or admittance prime times V of Z. So this is a shunt admittance per unit length, so to speak. Now, when you look at these equations, it's the same as before, but now instead of having constant impedances and admittances, we have impedances that have a relationship to the frequency. There are some frequencies for which those impedances or admittances go to zero or go to infinity. That is, they resonate. And therefore, this can be taken to be it can be taken to be what? It can be taken to be a filter-like kind of transmission line. Say, for example, Y prime. We have this is a conductance per unit length. That is a capacitance per unit length. Therefore, this admittance Y prime is equivalent to a conductance in parallel with a capacitance. Okay? So we have a parallel combination of a resistance and a capacitance for us to get this value, okay, of gamma Y. If you look at the impedance Z prime, we see that this value, this is a constant divided by area, so to speak, and this is a conductance, and therefore 1 over conductance or 1 over admittance is the same as an impedance. And therefore we can see that this is an impedance or a capacitive kind of impedance in series with an inductance. Okay, so that's why we are calling them filter-like. So the transverse electric waves as well, we do similarly, just like before, but recall that h of z is not equal to 0, but E of z is equal to 0. This is not correct here. I should put it at Ez equal to 0 and h of z not equal to 0. And therefore, in this particular case, it's a magnetic field intensity that is going to be rotational. And just like we did before, we are going to define h of t as a gradient of a transverse or of a scalar magnetic potential phi of m. So we write it as h of t equal to the minus of gradient of phi of m, and we start putting in the issues or the values. Transverse component of the electric field intensity must therefore satisfy the equation that equation there is correct. And from the reduced Maxwell's equation where E of z is equal to 0 must be, is just left with this component that is from the axial magnetic field intensity. And therefore, we can equate those values together. And what we get is that we now again drop the z cap and the z cap cross, and we are left with such an equation that is easily seen to be very similar to the other one before. So what we have done is that instead of removing what we had before, now we have just removed this value here of j omega mu over kc squared out there. And this, for obvious reasons, we are going to show that we can now interpret this omega, okay, omega mu by kc squared multiplied by that as a voltage, because this will have the values of impedance multiplied by distance, okay? That is impedance multiplied by length, that is current divided by length, and therefore when we multiply those two together, we get a voltage here. So this is going to be an important kind of interpretation that we shall see in the following. Again, this would be an inductive impedance down here at the bottom, and that is a conductance or an admittance. And therefore, all we are saying that this is a parallel combination of an inductive impedance and capacitive, lossy capacitance, capacitive admittance. So this will be a parallel combination. So we can therefore have that the minus gamma of that is equal to that, and therefore we get left with that equation, which is like similar to the other one, and we make the interpretation as follows. The reason why we are doing this is that k of c square has dimensions of reciprocal of area, and therefore j omega mu divided by kc squared has dimensions of the impedance multiplied by length. And therefore, h of z is going to be a voltage, and we can therefore write that dz of I of z is equal to the minus of y cap E of z, or where I of z is by definition given by phi of m, E of z is by definition given by j omega mu by kc squared multiplied by h of z, and y is going to be given by kc squared by j omega mu plus j omega epsilon. And we see it's a shunt admittance per unit length. So, and similarly, for the E of t, we can do the same. And what we get in the end is that equation there, which we can write immediately as shown, and we get that the derivative of the voltage is equal to the minus j omega mu multiplied by the current, and therefore we have that kind of equation where z prime is just going to be given by j omega mu as a series impedance of that per unit length for the medium itself. And therefore, if we look at this, we see that the voltage and current waves will be propagating again on a transmission line, filter-like transmission line. So when the problems cannot be satisfied by TE or TM waves alone, then we must have the mixed ones, but we can always decompose the problems into transverse electric and transverse magnetic and solve them, then use superposition to get the general solution. So this reduced form of the derivation is very important in our analysis. So the resulting general solution will be described as a hybrid wave. Okay, it has both characteristics of TE and TM. And this will always occur where we have the material having properties that are discontinuous. Now, another problem we can have is what we call the continuity equation. This is a statement of conservation of charge, which is a physical kind of requirement. So the time rate of flow of charge out of a closed volume V through the bounding surface, closed surface S, must be equal to the time rate of decrease of that charge enclosed within V if we require that V contains no sinks, that is where charge can flow into, or sources where charge that is producing a charge. That is, we just define a volume in space and then start looking at how, that is, we measure what charge is living out there, and then we know that as long as there are no sources in there and no other things that can take those charges, then the rate of decrease of that volume, charge in that volume, must be equal to the current or the flow, the rate of flow of that charge out of the volume. And this is therefore the principle of conservation of charge. And we can see that if we were to say that J, that is the conduction current density J, is the current flux through S, and rho is the net free charge density inside the V, then if we take the surface integral, the closed surface integral of the current flux, where flux is per unit length, per unit area, per unit time, then we can get it as equal to the minus d dt of the integral of V by rho of dV, so to speak. So we invoke the divergence theorem on the left-hand side, and we write the following, that remember the divergence theorem said that a closed surface integral can be converted to a volume integral by just integrating the normal component of the divergence of that field, and therefore the divergence of J plus d over d rho over t is equal to 0. That's all it means. We take these values, that is, we reduce this to the divergence, the integral over the volume of the divergence of J, okay, dV, is equal to the minus of d dt of the volume integral of rho of dV, and we see that since V is going to be arbitrary, so long as S is the boundary, then we can drop the integral signs and therefore get the point forms in that form. So the divergence of the curl of a vector field is also going to be equal to identically 0. That is, the divergence of a field that is the curl of another vector field is identically equal to 0. Just like we say that the curl of the gradient of a vector that is a gradient of a scalar potential is identically 0, this statement also is an identity, a vector identity, which we can always prove. So, from Ampere's circuit law, the divergence of the curl of H must therefore vanish, and therefore if we take that, the divergence of the curl of H must be equal to the divergence of D, the time derivative of the electric displacement plus the conduction current density. And once we do that, we get it as, we spread the we say that the time derivative and the spatial derivative can be, the order does not matter, so we can just throw it in and we get the divergence of D plus the divergence of that. But if you recall, the divergence of D was equal to the volume charge density, rho. And therefore, we can write it as, from Gauss' law, that the time derivative of rho plus the gradient and the divergence of J is equal to 0. Now, if the medium is linear and has constitutive parameters mu, epsilon, and sigma, and it's carrying a conduction current of density J, then we can replace, we know that J is going to be equal to sigma multiplied by E, or sigma divided by epsilon multiplied by D. And therefore, the divergence of J will just be given by that value there. So we see that the d dt of rho is equal to epsilon by rho, I think that divided by sigma is equal to 0, so to speak, where J is equal to sigma of E and D is equal to epsilon multiplied by E, so to speak. So this equation, we have solved it in many cases, especially in physical electronics, where we were dealing with the equations of the Poisson's equations and the likes, and this is called the continuity equation for charge. Okay, it has a solution. Okay, when the fields are time varying, rho and J are therefore related through this equation, and therefore most of the equations that we have are no longer independent and can be obtained from the others. And therefore, in the Maxwell's equations, the most important equations that we deal with are the Faraday's law of induction and the Ampere's circuit or law. All the others can be obtained from that using the constitutive parameter or the constitutive relations of that. The continuity equation can be obtained from that value, so to speak. So, when we deal with the constitutive relations, we can always group these into two sets. One, sets that are description relationships between the electromagnetic field quantities. And two, description of the mechanical interactions between the fields and the resulting secondary sources, that is, induced sources arising from the impressed sources. Now, the sets will depend on the properties of the medium that is supporting the electromagnetic field. And when we are constructing these constitutive relations, we must follow the following criteria. One, we must always think of the consistency with the basic conservation laws of nature. That is, charge must be conserved in that particular material. If you get a constitutive relation that does not conserve charge, then that constitutive relation is not correct. Two, the properties should not vary with the choice of the coordinate system. That is, if I chose to solve my problem using the Cartesian coordinate system, I shouldn't get a different answer from one who chose to use the spherical or the cylindrical coordinate system. The solutions should be the same. Isotropy or allotropy, that is the dependence on the orientation. If you get a different solution facing east than from the solution you obtain facing north, then that will be called allotropy. That is, there is a difference in the quality in the different directions. But if it's isotropic, then it means that the solution is the same everywhere. Such kind of materials where we have this kind of direction problems will be called allotropic materials, but we are not going to be dealing with them. Most of the materials we shall deal with are those ones whose the properties do not depend on direction. The relations must also be just setting. That is, the constitutive parameters that we use give us a unique solution. We don't want to have solutions that depend on who solved or the way the constitution parameter was defined. That is, once we use our constitutive relation, the solution is going to be unique and it's going to be the only one for the prevailing conditions set. It should also be dimensionally invariant, that is, or have similarity, and also material indifference, that is, it should not depend on who is doing the observation. It should be the same whether you observe it elsewhere by another person or if it's measured by a different kind of mode. Again, it must include all relevant physical parameter phenomena that are in that kind of material, and this should be the same across all disciplines of science. That is, if we make a relation that is only good for us in electrical engineering, but not good for those in physics or those in mechanical engineering and so forth, then that sort of relation is not proper. It does not show equipresence, so to speak. So the constitutive relations will generally consist of, one, a set of constitutive parameters, such as the mu, epsilon, and sigma that we've just seen, and two, a set of constitutive operators, either a gradient or a derivative or an integration, okay, or an addition or a multiplication, okay? So a medium then will be defined as homogeneous if in a given region of the medium, the constitutive parameters are spatially constant. That is, they don't depend on the position or the within the medium in that region. They are constant, okay, with respect to the spatial derivatives or integration. The material is stationary, that is, does not depend on time if its constitutive parameters are time independent. Then it will be temporally dispersive if the constitutive parameters or operators will include derivatives or integrals of time. Okay? Spatially dispersive if the operators include spatial derivatives or integrals. So the constitutive parameters may depend on other physical properties in the medium, e.g., temperature, mechanical stress, isometric state. Mechanical stress, you know, I'm sure you have met the concept of piezoelectricity, pyroelectric effects. Piezoelectric effects, this is mechanical pressure, that pyroelectric is dependent on heat. Isometric state, that is which direction it is. And we note that mechanical properties may depend on electromagnetic properties as well. That is, piezoelectricity is reversible. We can apply an electric field to a crystal and cause mechanical strain, or we can place a mechanical strain on the crystal and generate electrical charges. And this is what is called the principle of equipresence, or all those kind of things. So if we are going to classify the materials by their electromagnetic effects, the materials then they separate into linear and nonlinear materials through the manner in which the fields in the medium are related. Isotropic materials in which D is related to E, B to H, and J to E in a linear way, and they are all pairwise aligned. That is, they can be generated in the same direction, so to speak. They are parallel to each other. So anisotropic materials in which the field pairing would be the same as in the isotropic materials, but the fields in each pair are not aligned in general. That is, if D is facing north, E could be facing northwest or something like that. And in such cases, The parameters or the constitutive parameters are what we said before are going to be represented by what we call a tensor. Bi-isotropic materials include chiral materials. By chiral, we mean right or left-handedness. Of the most important for us would be DNA, especially for those of us who choose to follow a career in medical engineering, biomedical engineering. You may have to deal with the DNA that has a bi-isotropic kind of property. That is, the mirror images of the materials or the molecules are not identical. This you can recall from your course in organic chemistry in high school. So in a DNA, D and B will depend on both E and H, but with no realignment of E or H. By anisotropic material, they exhibit the most general behavior with D and H depending on both E and B, and the alignment of either of both fields is arbitrary. So from experiment, Röntgen, the discoverer of X-rays, showed that a material that is isotropic in its own frame of reference, that is laboratory or non-moving frame of reference, will be anisotropic when we view it from a moving frame. That is, if we have a coordinate system that is moving and we try to measure or to characterize a material that is in a stationary frame, then the material will appear to us to be anisotropic, which is the general case. And based on symmetry, Curie, the discoverer of radioactivity, predicted that an electric field in a stationary medium may generate magnetic effects, and magnetic fields produce electric effects, okay, in the magnetoelectric effects. These are called magnetoelectric effects, okay? That is, the electric field in a stationary medium may generate those, just like Faraday talked about the induction of magnetic fields or electric fields from magnetic fields. So the most general forms of constitutive relations between fields will be expressed symbolically as shown, that D is a function of E and B, and H is a function of E and B. That is, the E and B and A and L are taken as the independent variables, and then these are therefore defined from there. So B and H are called axial vectors, and E and D are called polar vectors because they depend on the position where they are being defined. They are not relative, while others are just pointing in the axial direction. So one of them is true vector, the other one is not a true vector. So by separation, Sommerfeld separated these fields into entities of intensity, which he took to be E and B. And this is in an answer that is a question that asks how strong, and a question of how much of that, which is that now the displacement and the magnetic field intensity. Answering that question, how much, how strong the electric strength or magnetic strength, or electric intensity and magnetic intensity. How much of that is it? So in this scheme, the E is therefore defined as electric field strength, B is a magnetic field strength, D is the electric excitation, and H is the magnetic excitation. Maxwell, on the other hand, separated this into a set E and H that appear within the line integrals that yield quantities related to work. We have seen that E, that is the line integral, the closed line integral of E, is equal to the time rate of change of the magnetic flux density. And the other one we saw that the closed line integral in Ampere's law of H is equal to that value of the current flowing. So this is the related to work. Now, accept B and D that appear in surface integrals and always yield quantities that are related to flux. Remember, flux is particles per unit area per unit time. That is, it's a flow of things, a flow of quantities, so to speak. And so in the Maxwell's separation, it's what we always use, and E now has the connotation, or is denoted as electric field intensity, magnetic flux density, and D is flux density or electric flux density or just electric displacement, and H is magnetic field intensity. So those are the things that we have for this particular thing. And we shall be using this definition from Maxwell, although we shall always put them in the Sommerfeld kind of way. So H and D are then defined in terms of polarization of the material and the fundamental field quantities B and E as in the Sommerfeld separation. So an electric field, when applied to a material body, will induce a distortion on the spherical charge distribution on the material atoms or molecules. And this distortion will then create an electric dipole moment whose density P, or dipole moments per unit volume, will be called a polarization. So the total charge density in a volume V that is bounded by a surface S due to the polarization will therefore be the sum of the bound surface charge density that is at the surface of the material will have some kind of residual polarization of charges and will be given as the normal component of the polarization P. And the volume bound charges is within the material, which will be given by rho P equal to minus the gradient or the divergence of P. Remember, we are saying they are bound, they are not moving for the material. If it's a dielectric, they won't be moving. Okay, but there will be separation of charge, but the charge does not move, and therefore does not cause any current. And this is the beginning of the displacement current that we've been talking about. And therefore, since the material or the medium is initially uncharged, the total charge enclosed in the volume must be equal to 0. And therefore, if we were to take the integrals, okay, of the bound charges, we can get, that is a surface bound charge and the volume bound charge. This must always be equal to 0 to show that the material is uncharged. We started with a neutral material and applied an electric field across the material. And therefore, the total charge out of the volume, then as a result of polarization, can therefore be given by Q integral, the surface integral of P of that, and it must be equal to that, and it must be equal to that value there. So, if P does not vanish, okay, if the polarization does not vanish, the bulk dielectric appears to be charged, and the total net charge must be 0 since the material is initially uncharged. Now, this will allow us to define now the electric displacement. Now, we can say that since a polarized medium gives rise to an equivalent volume charge density rho of P, E, due to the given source distribution, will be modified by the presence of the material. If we have measure E in vacuum, we'll get a given E. If we bring in now a dielectric in that region, the E that we measure must be different. That is, the distribution will change. So we express Gauss' law in the form that the divergence of E is equal to 1 over epsilon naught multiplying the volume free charge density rho that we had before, and we add to it a bound a bound charge density due to the polarization of the dielectric medium that we have introduced. So this is relation for the vacuum state or free state, and this is the free charge density, and that is the bound charge density. And this we have seen is equal to the minus divergence of the polarization of the material. And therefore, once we have that kind of thing, we can add those two, and we see that this divergence can be taken to the other side, and we multiply through by epsilon naught. This epsilon naught is a constant, so we have the divergence of epsilon naught multiplied by E, that is the free state, the displacement, plus the polarization of the material must be equal to rho, that is the free charge. And this equation in bracket is what we define as the electric displacement of the material. And therefore, the total displacement current is therefore the sum of the vacuum polarization displacement current as given as d dt of d is equal to d dt of the polarization plus d dt of epsilon naught multiplied by E. So this is the vacuum displacement, and that is the displacement due to polarization of the material. So in many materials, P and E are in the same direction, but will generally be out of phase in time phase. That is, they could be parallel in space, but they are out of phase time-wise. And therefore, we consider an atom that is polarized as shown. When the atom is, when the E is equal to 0, the charge distribution of the negative charge cloud and the nuclear positive charge have the same center of mass, and it's spherically distributed around it from Coulomb's law, which shows that there is symmetric or there's spherical symmetry about the atom itself because of the Coulombic attraction. Once we introduce an E, electrons try to move away from in the opposite direction to the applied electric field, and therefore we see an elongation of the atom. The atom now takes the form of a rugby ball rather than a soccer ball. Now, since electrons are lighter than the protons or than the nucleus, then we can always assume that the nucleus does not move, but it's only the cloud that displaces. And therefore, the centers of the negative and positive charges are now displaced by a small value of displacement, which we are here calling x. And this can therefore be modeled as a positive charge and a negative total charge displaced by a distance x. And if we multiply the charge by the distance, we get what we call a dipole moment. So this is the dipole moment we are talking about when the material is polarized by application of an electric field. So the center of mass is displaced, as we have said, with respect to the nucleus. And therefore, the electrostatic force that will be opposing this displacement can be modeled as using the Hooke's law. That is, if the x is small enough, then the force of attraction trying to pull back the electrons back toward the equilibrium position will be a stiffness S multiplied by x, just like a spring, okay? And we can say that that is the restoring force, the force trying to bring back the equilibrium conditions. So, because the field may be moving or may be changing direction in time, then we can see that there will be changes in the polarization direction. And if, as the atom is trying to change this, there is dissipative effects in the atom, we can always account for this by introducing a damping term, just like the force of friction, into the equation. And we get this displacement per unit time, which is a velocity. It's proportional to velocity, just like resistance is proportional to the derivative of charge. So let M be the effective mass of the electron cloud. We are not saying it's one electron, but it's a cloud of electrons in that atom. And we take the collection to have a mass, a total mass of m. So if we assume the motion of the nucleus to be small, because of the small value of their larger mass relative to electrons, then the equation of motion can be expressed in that form. That is m d2x dt squared, that is mass times acceleration from Newton's law of the second law of motion, plus the damping from the frictional force, plus the restoring force must be equal to the electrostatic force or the electric force that we have applied there due to the applied electric field E. And we are using the minus Q of E there. So we assume that the applied electric field, this minus Q is of course because of the electronic charge, it's an electron we are dealing with. So the applied field has a phasor form given by E of x multiplied by the exponent of j omega t. E of x could be real or a phasor value, but we are assuming that we have no phase. The phase reference is equal to 0. So if we are to place this value in here, then a possible solution to this equation of motion would be of the form x equal to x naught, the exponent of j omega t, where x naught is the position when the E is equal to 0. Okay, the displacement that would have. If the displacement was 0, of course, it also would have be real. If it's not 0, then we'll have a phase angle between x and E. Thus, when we use this in the equation of motion and solve, this is what we get. We get that the omega minus omega squared m plus j omega zeta plus s and multiplied by that phasor value is equal to minus q of E of x. This gives us a nice equation where we can divide through by m, and then we can take the values as shown there, and we get a value for the x naught as given by that. And because of this damping term, then x naught will have a phase angle in relation. So we can replace it by an omega p, where we define omega p as the square root of the spring stiffness divided by the mass, and we call it the natural frequency of the system. So before I go on, I think my time is even almost up. So do we have any question? Because I may be going too fast. No, you are happy?
Yes, no question.
Yeah? No question. So then I think then I'll just complete what I want to say. I'm going too fast. Is Wambua saying I'm going too fast? I don't know. Wow. So I'll try to reduce my speed a little bit. And what I want to say is that I just want to leave this at a good position. I see we have 17 minutes. I'll just take maybe 5 minutes, then we can break for the weekend and give you time to try and absorb that. So the dipole moment for a single molecule or atom in phasor form, we said, is just the positive charge multiplied by the displacement, and x we have seen is a phasor. So P of s is going to be given by Q multiplied by x. So when we have n dipoles per unit volume, that is n atoms per unit volume, and therefore they are all displaced, what we'll get is an npx, and therefore we multiply that nq and x of p. And therefore, when we place this in the equation that we already solved for p of x, that is, we replace the value of x, we get that p of x just going to be given by that value there. So the electric displacement is therefore going to be given by the volume or the vacuum displacement plus the displacement due to polarization. So we are just going to add those two, and what we get is just 1 plus chi of E multiplied by epsilon Ex. Chi is just going to be given by this expression here, and it's usually defined as the electric susceptibility of the medium. This is an equation that you may have met before. So when the medium is linear, that is, by linear we mean that if I double E, I double the polarization, then it means that the P is just going to be given by epsilon not multiplied by chi of E and multiplied by that E. And therefore D is just going to be given by that value E naught, that is the vacuum, plus the polarization, and we get an epsilon naught into 1 plus chi of E multiplied by E. And once we have that, we define this as electric permeability or permittivity of the material and give it the symbol epsilon. That is, we define, okay, the electric permittivity for the medium as epsilon equal to a real part of the whatever of the epsilon itself minus an imaginary part due to the J part. We know that chi is a complex number, and this is because of the dissipation due to the damping forces during polarization, and we can write that as epsilon naught into 1 plus chi of E. The imaginary part must always be negative so that it represents a loss of energy in that material. That is, there will be dissipation or Joule's heating due to the polarization or the damping effects. So this loss in the medium could arise from the damping or the non-zero conductivity of the material, but the effects, as far as we are concerned, just like in the microwave oven, we use this kind of principle, that is, we are polarizing the food and using the damping forces to do the heating. So the material could be conductive, or it could be because of the damping in the polarization. So as far as externally we are concerned, the dissipation just appears to us as heat, and therefore you can say this is heat due to current flow through a resistance, or it's the damping effect in the polarization. So we call them indistinguishable. And therefore in the Ampere's circuit law, where we had sigma plus j omega epsilon plus sigma, now we are replacing the epsilon in the circuit law with its definition and adding them out, and we see that we have this expression here as plus sigma equal to E. So the loss in the medium is often defined through the loss tangent, which is defined by the tangent of sigma over delta L equal to omega prime double prime plus sigma over omega epsilon prime, the real part of the permittivity. And note that at very high frequencies, especially those ones encountered in microwave ranges, that is 10 to the 9 of hertz, then omega epsilon double prime may be much larger than sigma. And in such cases, we can always take that omega multiplied by epsilon double prime plus sigma is an effective conductivity which can be represented by a single parameter epsilon double prime equal to sigma by omega, or sigma equal to omega double prime, and therefore we write, okay, we write these losses either, so we can write it as the tangent of delta L equal to epsilon double prime over epsilon prime, or sigma over omega epsilon double prime. And epsilon double prime or sigma contain both conduction and damping losses that we have in the medium. And that's how we are going to look at it. For an isotropic media, we say that D and E are not aligned, and we can have a dx, dy, and dz, and it's related to ex, ey, and ez by the matrix of the permittivity. This is what we call a tensor, and it's a 3x3 tensor that relates those two. In some of the media, we can always define a principal axis, just like those crystals that we used in high school that were giving us double reflection. We could always define an axis, a principal axis, x prime, y prime, and z prime, which will diagonalize this particular tensor. And in the end, if that's the case, we can always get dx prime, dy prime, and dz prime related to ex prime, ey prime, and ez prime by that simple relation there, where the matrix now is just a diagonal matrix rather than a 9 by 9, kind of components. And the medium is therefore going to be described as biaxial if E11, E22, and E33 are all different. It is uniaxial if E1 and E2 are equal, but E3 is not, E33 is not equal to them. It is going to be called isotropic if E11, E22, and E33 are all equal to a constant E, epsilon. So with that, I think we can continue from there next time when we look at the constitutive relations for the H field. But this is not much really left. So remind me next time to try and be a little bit slower. But usually you find that since I'm not writing on the board, it's much easier. It's just, my tongue is easier than my hand. So it's much easier to talk. Or would it, well, I'll send the recording. The slides, I thought, since I'm discovering problems in typos as I go along, if I send the slides now, what will happen is that at the end of it all, I'll have to send you again the corrected version. And that's why I was requesting that we follow. You can try to work with the ones that we have already done with the video and the lights. But at the end of this particular type, we now have a few more slides to go. I think 72 slides to go. And then I'll send this to you, a corrected version. Okay? That would be much better for me. And I guess for you as well. You don't have to inherit my mistakes inside. Whatever the slides. Is that okay with everyone? Okay, fine. So I wish you a nice day and do have a nice weekend. Thank you for listening.